Good morning, guys. So a handful of things to do today. I'm going to go ahead and jump right in. So first things first, I owe you guys an apology. I haven't finished grading your tests yet. I've had a few things come up that have made this process a lot slower and a lot more of a pain in the ass than it normally is. But I should get them wrapped up today. So I know I've taken longer than I said I would take, and I know that that's frustrating from your end. I want to apologize for that. One of my sections had a rampant cheating issue, and I've had to spend a lot of time yesterday and the day before dealing with that. But I'll be getting through the rest of these later today. That's the plan. So sorry about that, and I appreciate your patience. Today we're going to talk more about sequences. Particularly, we're going to learn about limits and convergence. We'll look at the graphs of sequences. We'll introduce the notion of convergence for sequences, which is intimately tied to the concept of a limit of sequences. And then we're going to start developing some theorems and other results about sequences. So we're all still in section 11.1. 11.1 is a very theorem-heavy section. So let's get started. Remember, we said that a sequence is a function whose domain is the positive whole numbers, maybe including 0, maybe not. So what does that say about the graph? Well, remember, you can find the domain of a function by like squeezing the graph down onto the x-axis. Right? You take the whole graph, you smush it down onto the x-axis. Those x values that get hit, those are the domain. So if the domain of your function is just the whole numbers, then when you squeeze the graph down, you should just be hitting the whole numbers, which means that the graph can't possibly be like a curve. It can't possibly be continuous in any way. It has to be just a collection of discrete points. And indeed, that's what the graphs of sequences look like. So the graph of a sequence the graph of a sequence looks something like this. It's made up of input-output pairs, so like 1, A1, 2, A2, 3, A3, and so on. Something like this. So the y value of each of these points is the value of that term of the sequence. So like if A1 is 1, then this would be the point 1, 1. If A2 is 1/5, then this would be the point 2, 1/5. But in general, the graph of a sequence is just a collection of dots like this, which might make you wonder, why the hell do we study something like this in calculus? In calculus, we're interested in like continuity and areas and tangent lines, slopes, and sequences have none of that, right? You can't talk about like a tangent to the curve here because there's no curve. You can't talk about the area under the curve because, again, there's no curve. You can't talk about continuity or differentiability because these things are separate individual points. So there's no way to talk about continuity. This thing is about as far from being continuous as any object can be. There's one calculus operation you can still do. And that's take limits at infinity. So, graph of a sequence looks like this, right? Just those dots. And the only calculus operation we could hope to do with something like this is take the limit as n goes to infinity. So here, if these dots were all to get closer and closer and closer to that horizontal blue line y equals L, then I would say the limit as n goes to infinity of an is L, because these points are all getting closer and closer and closer to L, and they're staying close to L. I'll give you a strict definition here in just a second, but before I do that, I want to look at a graph of a few other sequences. So let's sketch the graph of the sequence an equals 1 over n, where n starts at 1. So here I have my n axis. This is my an axis. And I'm going to mark this all the way up here as 1. I know that a1 is 1. Right? If you plug in n equals 1 here, 1 over 1 is 1. That tells me that the point 1, comma 1 is on the graph. Right? Input-output pairs, just like for regular functions. A2 is 1/2. Tells me that the point 2, comma 1/2 is on the graph. A3 is 1/3. This tells me that the point 3, comma 1/3 is on the graph. A4 is 1/4. So the point 4, comma 1/4 is on the graph. And then 5, comma 1/5, 6, comma 1/6, and so on. Any questions about how I drew this graph or why this is the graph of 1 over n? Here you may notice that these dots are all kind of getting closer and closer to something. As we go further and further to the right, these dots are all getting closer and closer and closer to the horizontal axis. In other words, the output for this sequence is getting closer and closer to 0. as n gets larger and larger. This brings us to the concept of a limit of a sequence. So this is the graph an equals 1 over n. I told you that we're going to have several different notions of convergence. Right? We have an idea of what it means for an improper integral to converge. The next thing we're going to talk about converging is a sequence. So we say that the sequence, and when I want to refer to a sequence as a singular object, right, all the terms at once, I put it in curly braces like this. We say that the sequence an converges provided the limit as n goes to infinity of an exists and is finite. So kind of similar in a sense to the improper integral thing. You have an infinite process leading to a finite result. That's what it means for the sequence to converge. But of course, very different than improper integrals, because here I'm not talking about area, I'm not talking about integrals, it's a whole different ballgame. But we still use the word converge. We say that an diverges if lim n to infinity an does not exist or is not finite. That's all. So this is kind of the easiest notion of convergence to wrap your head around. Of course, the thing you need is the concept of a limit for a sequence. And the good news is that limits at infinity are limits at infinity, whether you're talking about functions or sequences. Same thing. So all of the rules that you learned for calculating limits as x goes to infinity, you can use those same rules for calculating limits as n goes to infinity. And the x to infinity limits, that's stuff you learned in Calc 1, way back in section 2.6 of the textbook. I'll do my best to kind of remind you the stuff that hopefully you learned in Calc 1. But first, I need to give you the strict definition. Actually, I'm going to give you two definitions, one kind of intuitive and one rigorous. So here we're defining the limit of a sequence. We say that lim n to infinity of an equals L if as n gets bigger and bigger, the terms of the sequence get closer and closer to L. That's all. So I think this is probably the definition that you're used to thinking about for limits of continuous functions. Another way to say this is we can make AN as close as you want to L by taking N sufficiently large. All right. These are both intuitive definitions, or these are both intuitive phrasings of a rigorous definition that I'm going to give you in a minute. Well, the picture here is the one that I drew on the previous page. All right. Here, the terms of this sequence, these dots, are getting closer and closer and closer to L. And they're staying close. So I would say, I can make these dots as close as you want to L just by going far enough to the right, by taking N sufficiently large. The rigorous definition same thing though, limit of a sequence. Here we say, same thing, lim n to infinity, an equals L, if for every number epsilon, which is greater than 0, so for every positive number epsilon, there is a number capital N such that an minus L has size smaller than epsilon, provided little n is bigger than capital N. This definition tends to scare calc students because you're not used to working with epsilons. And that's okay. I'm not going to make you work with this second definition, but I do want you to try and see what it says. So I'm going to draw in the horizontal line y equals L. I'm going to draw in an epsilon window about L. So the vertical distance between the dotted line and the solid line is epsilon. What this definition says is that, sure, an, the terms of the sequence might do all sorts of stuff at first. Maybe I start off down here. But eventually, at some n value, I pass into this epsilon window. And then forever after then, I stay inside this epsilon window. Another way of saying this is that only finitely many terms of the sequence are outside this window, no matter how narrow it is. So up here, this would be L plus epsilon. Down here, this would be L minus epsilon. So no matter, kind of third way of thinking about it, no matter how narrow the epsilon window is, all but finitely many terms are inside it. So there's finitely many terms before this, right? Capital N minus one of them. There's infinitely many terms inside of it. The important thing here is that no matter how tight I shrink this window, there will only be finitely many terms outside if the sequence AN converges to L. So that's what it means for a sequence to have a limit. And while this might look new and scary, it is in fact the exact same thing you learned in section 2.6 of Calc 1. And the good news is that all the shit you learned for taking limits there works great here too. So this is great. This is a bunch of word soup. What does it mean for us? Well, a sequence converges if it has a finite limit. So you need to learn how to take limits of sequences. But since this definition is the same as the definition for continuous functions, you can use all the tricks for limits of sequences that you learned for limits of continuous functions. And that's actually our first theorem. I'll give you a second to write.
What does the last sentence says?
Down here,
Yeah.
it says, no matter how narrow the epsilon window is, all but finitely many terms are inside of it. So this window right here, like the dotted lines, that's our epsilon window. Call that an epsilon window about L. No matter how narrow I make this, like if I were to shrink it like this, still all but finitely many terms of the sequence are trapped inside of it. So that's what it means for the limit as n goes to infinity of AN to be equal to L.
Wait, so what is epsilon?
Epsilon is an arbitrary positive real number. So the way these sort of things work, God hands you epsilon, right? You say, I've got this sequence. I think its limit is 5. God hands you epsilon and says, okay, can you show me that no matter how tight my epsilon window about 5 is, that all but finitely many terms of the sequence are trapped inside there? So epsilon is a positive real number over which you have no control. We call those arbitrary positive real numbers. The textbook has some pictures that are pretty good. I can pop those up for you for just a second. Let's see here. Oh, shit. Come here, come here. It's going a little too fast. Let me be good. Right, so here's some pictures of a sequence converging to L. And the idea is that no matter how tight I were to draw a little window around L, only finitely many terms of the sequence are outside of it. Here you see the rigorous definition. And if we're lucky, they'll have a good picture explaining, yeah, here it is, right? So at the start, maybe my sequence does all sorts of stuff, but eventually it falls into this window. And forevermore after that, it stays inside that window. And the idea is that since you don't have control over epsilon, this window could be very, very small. And you have to prove that no matter how small the window, there is some number capital N, so that all the terms to the right of that number are trapped inside this window. Now, in practice, I can't make you use this definition because I know most calc students are not anywhere near ready to work directly with that definition. I can invite you to compare it to what you were learning back in Calc 1 when you talked about horizontal asymptotes and limits at infinity. Here you will see, did they do it? I think they give the rigorous definition here somewhere. Maybe not. Looks like they're afraid. Yeah, okay. There it is. Yeah, here we go, right? So if you go to the right of cap n, the graph stays inside this window. Compare that to the picture for sequences. It's really the exact same thing, right? Only instead of having a curve, when you talk about sequences, you just have a few dots. The good news is that because these definitions are the same, all of the tricks you learned back in 2.6 can be applied to sequences. And what our very first theorem here says is that if the sequence an is coming from some nice function f, where f of x is a continuous function, regular, doesn't even actually need to be continuous function, then the limit as n goes to infinity of an is equal to the limit as x goes to infinity of f of x. So let me show you an example. Let's find the limit as n goes to infinity of the inverse tangent of n. Well, here f of x is equal to the inverse tangent of x. I can relate the sequence inverse tangent n to the function inverse tangent x. And I know what the graph of arctan x looks like. Hopefully by now we've beat on this enough in this class. Like 1, 2, 3, 4, 5, 6, and so on. So my sequence are these dots, just the dots. But since the function is going to pi over 2, and the sequence is trapped along the graph of the function, the limit as n goes to infinity of the inverse tangent of n is equal to the limit as x goes to infinity of the inverse tangent of x. And that limit we know from Calc 1 is pi over 2. Does this make sense? Another kind of example like this is if I wanted to find the limit as n goes to infinity of 1 over n. Well, if I swap the n's for x's there, then f of x is 1 over x. And I know what the graph of 1 over x looks like. It looks like this. So if here's 1, 2, 3, 4, 5, and so on, then here's the sequence 1 over n. It's dots that are trapped along this curve. And here again, the limit as n goes to infinity of 1 over n, the limit of that sequence has to be the same as the limit as x goes to infinity of 1 over x. And I know that the limit of 1 over x as x goes to infinity, that's 1 over infinity, that's 0. So the limit 1 over n is 0 as well. So both of these sequences that I'm talking about converge. In this first guy, I would say, therefore, the sequence an equals inverse tangent of n converges to pi over 2. And in the second example, I would say, therefore, the sequence an equals 1 over n converges to 0. Why do the sequences converge? Because the limit of the sequence does exist and it is finite. The limit of this first sequence is pi over 2. Pi over 2 is a finite number. So the sequence an equals inverse tangent of n has a finite limit. Therefore, I say that sequence converges. And the language we use here, we say the sequence converges to pi over 2. Making sense? Snap two things. Okay, any questions on either of these examples? Okay. A sort of corollary to this theorem, a consequence of this theorem, could say, recall that for any positive number p, the limit as x goes to infinity of 1 over x to the p is 0. Thus, by our theorem, the limit as n goes to infinity of 1 over n to the p is also equal to 0 for any positive number p. This is a useful fact. Right? We'll use this quite a lot. The intuition here is very clear. If p is positive, then n to the p gets big as n gets big. And if you take the reciprocal of something that's very, very big, you get something that's very, very small. So you get like 1 over infinity is 0. This is something hopefully we're all familiar with. There's a trick associated with this, and it's probably the most important trick for limits of sequences. We call it renormalization. I'll show you through an example. If I want to take the limit as n goes to infinity of 5n cubed minus 2n squared plus the square root of n all over 2n cubed plus 4n minus 3. If you try to just plug in infinity, if you swap the n's for x's and then try to plug in infinity, you get infinity over infinity. You could use L'Hopital's rule on that. We haven't talked about L'Hopital's rule yet, but you could. But L'Hopital's rule sucks. We don't want to use L'Hopital's rule unless we absolutely have to. Here it would take several runs of L'Hopital's rule to get the job done. The renormalization trick is much simpler. You just divide top and bottom by the largest power of n. So here the largest power of n is 3. I'm looking at both the top and the bottom there. The largest power of n I see anywhere is n cubed. So I'm going to renormalize this expression by dividing top and bottom by n cubed. So I rewrite, this is equal to the limit as n goes to infinity of 5n cubed minus 2n squared plus, that's n to the 1/2, all divided by n cubed, over 2n cubed plus 4n minus 3, all divided by n cubed. Now when you distribute that n cubed, the 1 over n cubed downstairs there, and upstairs here, you get lim n to infinity 5 minus 2 over n plus 1 over n to the 5/2 divided by 2 plus 4 over n squared minus 3 over n cubed. And now, according to this result, all of the non-constant terms in this expression go to 0. 2 over n goes to 0, there p is 1. 1 over n to the 5/2 goes to 0, there p is 5/2. 4 over n squared goes to 0. 3 over n cubed goes to 0. So this whole sumbitch goes to 5/2. That's it. Because all these pieces go to 0. This renormalization trick is how you prove that rule that you learned for finding horizontal asymptotes way back in college algebra, where you compare the degree of the top and the bottom. Only this renormalization trick also works for stuff that has square roots, also works for things that are not rational functions. So it's a good trick, and it is definitely the most important trick for limits of sequences. It's the trick you'll use more often than anything else. Questions on this example? Okay. Okay. So what to do next? I want to show you an example of a limit being bad. One of the sequences we looked at last time was the -1 to the n sequence. I can't use my swap n with x trick here. Here, the function I get if I replace n by x, -1 to the x, is definitely not continuous. In fact, it's horrible. Fuck this thing. Seriously. Like f of 1/2 here is the square root of -1 is I. F of 2/3 here is 1. F of, say, 3/2 here is -I. And good luck finding anything like f of pi or f of the square root of 2. Like, what the hell is -1 raised to the pi or -1 raised to the root 2? No, just no. We are not going to be able to swap the n for x and then use old tricks here. But if you look at the graph, if you look at the graph of -1 to the n, you'll be able to tell me about this limit, no problem, I suspect. Remember, -1 to the 1, that's -1. -1 to the 2, that's +1. -1 to the 3, that's -1. -1 to the 4, that's +1. -1 to the 5, that's -1. -1 to the 6, that's +1 again. So does this sequence have a limit? I'd like to see some thoughts. Here's some comments. Does this have a limit? What would be some reasonable possibilities for this limit? Well, it's a piecewise constant sequence. It only ever outputs two numbers, 1 or -1. Are these dots getting closer and closer and closer to some particular y value?
No.
No. And the only things that you could even put forward as possible limits here are either 1 or -1 itself. So let's see, if I draw an epsilon window about +1, is it the case that eventually all the terms will be trapped in this window? Is there some point after which all of the terms will be trapped in this window?
I'd
Yes
say
or no?
no.
Hell no, right? Half the terms are down here, right? No matter how far you look, there's always going to be other terms down there. And if you tried to draw that same sort of window around -1, the same problem happens. You're always going to have other terms popping out of that window. So it certainly isn't 1, and it certainly isn't -1. This limit does not exist. There is no number L here, which satisfies that definition that all the terms eventually get close and stay close to L. Matthew asked an interesting question. Could 0 be a reasonable candidate for the limit here? If you average all these terms, then yeah, the limit of that sequence is 0. But that's not the definition of a limit, right? There is a concept like that, and what you're getting at there, Matthew, anybody else who's curious about this, or anybody who's listened to Tool, the band, Google Cesaro mean. So Cesaro summation and Cesaro limits are a way of taking sequences that don't converge and averaging them and seeing if that average converges. It's a cool concept, but it's not what we're doing here. So for us, not just for us, in general, here we would say that the sequence an equals -1 to the n diverges. Right? Because there is no limit. The limit does not exist. Remember, for a sequence to converge, the limit must exist and be finite. Otherwise, we say the sequence diverges. Okay, una más. What about the sequence an equals 1 minus e to the -n? Any ideas what I could do here?
Can you repeat that, please?
So I'd like to know whether this sequence converges or diverges. What should I do with it?
You could graph it.
I could. What does it mean for a sequence to converge? What sort of thing should
A
I be looking?
condenses into one number.
Yeah, the limit, right? It has a limit. So I
Correct.
should be looking for the limit as n goes to infinity of an, which here is the limit as n goes to infinity of 1 minus e to the -n. I could try graphing this, yeah. But let's try to work from a slightly higher level perspective. Which of our tricks do you think will work nicely here? Because I don't know what the graph of this looks like right away. It's not like -1 to the n where the graph is super easy to draw because the outputs are kind of weird. But one of the tricks we've already used today will work here. Is this something that's easy to renormalize? Do I have weird powers of n? n cubed, n squared, squared n, stuff like that I could divide out by to make this nicer?
Yes.
I would say no, right? There's nothing I can like divide top and bottom by here to renormalize. Also, this doesn't look like infinity over infinity or anything like that.
Right. Right.
But the very first trick, right? The swapping n's for x's trick. This will work nicely here because I know what e to the negative x does. I know what the graph of e to the negative x looks like. Or certainly you should know what the graph of e to the negative x looks like, because you've all taken at least one course in pre-calculus and at least one course in calculus. This is the graph y equals e to the negative x. And as x goes to infinity, where does e to the negative x go?
Closer and closer to 1. Sorry, maybe I misunderstood your question.
This
Or
is
just
0, 1 here.
Okay, so to 0.
Yeah, this goes to 0. So this is 1 minus 0, or 1. So the limit of the sequence an is 1. How did we get there? By thinking about the continuous function 1 minus e to the negative x. And then I just graphed here the e to the negative x part because I know what that part looks like, and that's the only part that makes this hard. So I would say that the sequence 1 minus e to the negative n converges to 1. So all of these things from section 2.6 in the textbook, you need to remember them. They're important. The limit of e to the negative x as x goes to infinity is in there in the textbook, along with the limit of like arctan and the 1 over x to the p rules. Those are all things that I'm supposed to assume you guys remember from Calc 1. Now, I know that life isn't like that. We forget shit, and sometimes we don't ever learn it in the first place. But you have just now run into the part of your lives where you cannot proceed without knowing that shit. So make sure you go back and reread 2.6 if you need to. Okay. Questions on either of these last two examples? So the first example, the swapping n for x trick didn't work. So we looked at the graph. The second example, the swapping n for x trick worked great because I know what the function e to the negative x does. Pay attention to the notation. Pay attention to how I'm writing things, right? Like this, you need to be writing things the same way. So make sure that your solutions are following the same, not just answers and results like mine, but make sure that your notation and your language is correct as well. Okay, any questions on why I wrote what I wrote or how we got the results we did? Any questions on why we say this first sequence diverges or why we say this second sequence converges to 1? The idea, Nathaniel, is that I know what this function looks like from my previous studies, right? Ever since college algebra, you guys have been playing with the function e to the negative x. According to the theorem, according to this theorem, if when you swap n for x, the resulting function is continuous, then you can take the limit of your sequence by taking the limit of that function instead. So this theorem gives me permission to swap n's for x's, as long as doing so results in a continuous function. And I want to do that anytime swapping n for x gives me something I know how to handle. And we should, from college algebra, pre-calculus, and calc 1, know what the graph of e to the negative x looks like. So even though I don't know shit about the sequence 1 minus e to the negative n, I do know exactly what the graph of e to the negative x looks like. That tells me I would like to swap n for x. And since 1 minus e to the negative x is a continuous function, this theorem gives me permission to do that, to swap the sequence for that continuous function in my limit. Since I then know from my previous classes how to take the limit of this thing, I do so. And according to my theorem, that's the same as the limit of my sequence. So we're changing the n to an x so that I can use all the stuff I learned in Calc 1 about limits at infinity. Does that answer the question? Do you feel comfy with that? Sweet. All right. One of the other things here, this means you can use L'Hopital's rule, right? If you've got a ratio like f over g, something like e to the x over x or x over e to the 2x, you would calculate the limit as x goes to infinity there using L'Hopital's rule. So if I asked you to calculate the limit of the sequence n over e to the n, you would swap the n's for x's and then apply L'Hopital's rule. It works great. All that stuff you learned in Calc 1, including the squeeze theorem, which we'll talk about not today, but on Friday, you can use here. But before we do that, I need to introduce a new family of sequences called recursive sequences. How many of you have heard of differential equations? It's a class offered here at Santa Fe. Very, very important in physics, right? If you've ever heard of Maxwell's equations, the equations that describe how electromagnetism and light behave, those are differential equations. Newton's laws, F equals ma, that's a differential equation. All the important laws from physics are differential equations. There is, just like, how do I say this? Just like sequences can be compared to continuous functions, so like there is a sequence version of every continuous function, you just replace the n with an x or the x with an n. There is a sequence version of differential equations called difference equations. Those are recursive sequences. So recursive sequences are the sequence version of differential equations, which means that all the important real-world applications of sequences are recursive, or at least most of them. The definition of a recursive sequence: a sequence defined by giving the first few terms and also a rule for calculating the next term as a combination of previous terms is called recursive. If you've ever done any programming, computer programming, you'll know what a recursion is. It's where you say, okay, yeah, to calculate the next thing, you mash up some combination of the previous things. These first few terms, these are called the initial conditions. And the rule for calculating the next term, this is called the recursion relation. There's one really famous example called the Fibonacci sequence, and I'll show you that, but there's an even more important example that I want to show you first. So I'm going to define the sequence AN by saying A0 is equal to 1 and an plus 1 is equal to n plus 1 times an. So this is your recursion relation, tells you how to get the next term from the previous term, and this is your initial condition. The whole of n plus 1 down here is in the subscript. I want to make that clear. So you can think of this as being like in parentheses down in the subscript. So like this is A3, this is A2. This is A7, this is A6. If I take this recursion relation, so I know that A0 is 1. This sequence starts at n equals 0. How would I figure out A1?
You plug in 1.
Well, I want to get A1 over here. So I would actually plug in 0 for n, because then I would have A sub 0 plus 1, which is A1. So if I plug in n equals 0 here, I'll get A1 equals 0 plus 1 times A0. Now 0 plus 1 is 1. So this is just 1 times A0. And A0 is 1. So this is just 1 times 1, which is still 1. A2, I would get by plugging in n equals 1 here. If I plug in n equals 1, I get A sub 1 plus 1, which is A2, equals 1 plus 1 times A1. 1 plus 1 is 2, so this is 2 times A1. And A1 is 1, so this is 2 times 1, which is 2. And the pattern continues like this. If I plug n equals 2 into my recurrence relation, I get A3 equals 2 plus 1 times A2, which is 3 times A2, which is 3 times 2, which is 6. If I plug in n equals 3, I get A4 equals 3 plus 1 times A3, which is 4 times A3, which is 4 times 6, which is 24. And I could keep going like this. So a recursive sequence is one where you don't have an explicit formula for an. Instead, you have a rule that tells you how to get the next term out of the previous terms. So if I wanted to find A10, I would have to calculate A9 first, because all this tells me is that A10 is equal to 10 times A9. Right? I could come down here and say, okay, A10 is equal to 9 plus 1 times A9, which is 10 times A9. But that shit doesn't help me unless I already know what A9 is. This is why we call them recursive, because they refer back to the previous thing. So I can't figure out what A10 is unless I already know A9. So I need A9 to find A10, which means when you calculate these, you have to go in order, right? You take your initial condition and you start calculating up from there. So the definition, a sequence defined by giving the first few terms and a rule for calculating the next term as a combination of the previous terms is called recursive. Now here I want to play a little bit more with the sequence AN that I've got in this example because like I said, this is a very important sequence. Turns out the sequence AN here counts something. It counts the number of ways you can arrange n-1 people in a circle. So like if you were bringing 10 people over for dinner, the number of ways you could sit them down at a circular dinner table would be A9. It's called the factorial sequence. And you may have seen another definition. So 2, of course, is 2 times 1. 6 is 3 times 2 times 1. 24 is 4 times 3 times 2 times 1. The next term in the sequence is 5 times 4 times 3 times 2 times 1. So here AN is called n factorial. And is usually denoted n with an exclamation mark after it. It's not typically defined recursively. Although the recursive definition is very useful, the definition that's usually given in pre-calculus classes is n factorial is n times n-1 times n-2 times all the way down to 3 times 2 times 1. So like 4 factorial is 4 times 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. It's a huge number. I'm not sure what 10 factorial is, right? 5 factorial is 120. 6 factorial is 720. They get really, really big, really, really fast. Oh, I did, didn't I? Yeah, 6 times 5 times 4 times 3 times 2 times 1. Yeah, thank you. Yeah, good catch, Connor. One of the things that we're going to be doing a lot of in this class is simplifying factorial expressions. So I wanted to give you a little bit of practice with that today before I let you go. How am I doing on time? 5 minutes. All right. So let's see if we can find the limit as n goes to infinity in n-1 factorial over n plus 1 factorial. Oh, Hammy, it's okay, baby boy. Sorry, my dog's gonna throw up here. That's a bummer. All right. this is equal to the limit as n goes to infinity of, what's the denominator? Well, n plus 1 factorial is like anything factorial. It's that thing times that thing minus 1. So n plus 1 minus 1 is just n. I'll rewrite this and zoom in big. So here, this is the limit as n goes to infinity of, we'll do the bottom first. N plus 1 factorial is n plus 1 times n times n minus 1 times n minus 2 times n minus 3 times, and you go all the way down to 1. So the factorial of anything is that thing times that thing minus 1 times that thing minus 2. It's the product of all the positive numbers less than or equal to that thing. So what is n minus 1 factorial? Well, that's going to be n minus 1, that thing itself, times what's the thing right below n minus 1? What's the next smallest number? Well, that's n minus 2 times, and then the next smallest number, that's n minus 3 times, and then the next smallest number, and then the next smallest number, all the way down to 3 times 2 times 1. So there's a lot of cancellation here. And all the stuff in these ellipses cancel. So here we would be left with limit n to infinity 1 over n plus 1 times n. Now n plus 1 and n both go to infinity as n goes to infinity. So this is 1 over infinity times infinity. Infinity times infinity is definitely infinity, and 1 over infinity, that's 0. So here, the limit that we were asked to calculate is 0. But this procedure of expanding and simplifying factorials, this is important. Not just for this section, but for the sections that come after. Not even just in the sequence chapter, but in the series chapter and in the power series chapter. All right, this is all we have time for today, so I'm gonna have to go ahead and end our meeting here. I appreciate you guys being patient with me getting the tests graded. Like I said, I've had a big problem with a massive cheating scandal that I'm doing my best to handle delicately. Yes, sure. If you need homework extensions or anything like that, go ahead and submit the requests and WebAssign. I'll go through and clear those out. But that is it for today. I will see you guys either in office hours or in our class meeting on Friday. On Friday, I'm going to show you a handful of other theorems on sequences. And then I'll introduce you a little bit to the material that we're going to start with on next week, which is series. Series, this hard section of this class, we're going to be moving fairly quickly through it. And it's going to be a lot of this sort of theorem logic stuff. So you need to be very, very careful. Remember what I said on Monday about sharing your results with people, talking, working together, making sure your logic is good. You need to be dumping time into the class right now. All right. So that's it. I'll see you guys Friday. Hope everybody has a lovely rest of your day. And take care.
Thank you so much, Professor. Have a good day.
Of course. You too.